Hello, welcome to my video series of algorithms. This is part 4 of Module 1, Sorting Algorithms. In the previous videos, we have discussed 3 sorting algorithms. They are selection sort, insertion sort, and bubble sort. All of them have an O(n) squared time complexity. In this video, we will present another sorting algorithm called shell sort, which can run faster than the existing O(n) squared time. Shell sort is named after its inventor, Dr. Donald Shell. The algorithm is also known as the diminishing increment sorting, which better describes the procedure it takes. As we proceed, it will be more clear to see why it is also called the name. Let's begin with motivating the main idea of the shell sort algorithm. Recall that insertion sort and bubble sort run in O(n) squared time in the worst case and O(n) in the best case. Know that by the worst case, we mean an input order that disfavors the corresponding algorithm, and by the best case, we mean that the input elements are already sorted. Therefore, it is intuitive to conjecture that when we make the input list partially sorted, we can sort it with a time complexity between O(n) and O(n) squared. Know that we lose when spending effort in making the input partially sorted, but gain when we sort faster with a better case input. The procedure and the analysis that together make the gain outweigh the loss is the essence of the shell sort algorithm. First, let's look at how shell sort partially sort the input. The algorithm contains several sorting phases, and in each phase, it tries to sort all numbers that are h apart. We will use insertion sort for this purpose. The parameter h is referred to as the increment. We refer to the sorting phase with the parameter h_sort. And we call this list of output by the h_sort phase h_sorted. Here, we have a list of elements that are 5 sorted. Different colors represent different sets of elements that are apart by 5 indexes. And you can verify that all numbers in the same color are sorted. For example, the red numbers 35, 41, and 81 are sorted. The blue numbers 17, 75, and 94 are sorted, and so on. Recall the name diminishing increment sorting. The increment h corresponds to the word increment in its name. Now, realize that after the h_sort phase, the list remains unsorted, unless h equals 1. But if we directly sort with h equal 1, we will not have a partially sorted better case input. To address the dilemma, we will use a series of diminishing increment values. Specifically, we will assign a large increment ht for the first sorting phase, a smaller increment ht-1 in the second sorting phase, and so on. In the last sorting phase, we must assign h1 as 1 to ensure that the entire list will be sorted. This procedure explains well the algorithm's name, diminishing increment sort. Recall that we have obtained the 5 sorted list from the previous example, and we can proceed with the 3 sort phase on the 5 sorted list. We begin with sorting the first set of elements that are apart by 3, which are highlighted in red here. We then sort the blue elements, and finally the white elements. At last, we will sort the elements with 1 sort, which applies insertion sort on the 3 sorted list. Notice that since the 3 sorted list is partially sorted, we can expect more pretermination cases compared to a random list. Here is the pseudocode of the shell sort algorithm. Note that the algorithm contains 3 for loops. The first for loop corresponds to different sorting phases. The second for loop considers each element AI in the list. And the third for loop tries to insert the element AI into its proper location among the former elements. Here is a visual illustration of the algorithm. This figure demonstrates a two-sort phase as an example. You can see that the index I loops through each element in the list. For element AI of interest, the algorithm tries to insert it among the former elements that are 2 apart. Now, let's analyze the correctness of the algorithm. The proof is trivial as the last sorting phase is one sort. By definition, a one-sorted list is a sorted list. Next, let's analyze its computational efficiency. We claim that the algorithm runs in O n to the power of 1.5. The proof of the time complexity is a bit involved, and we will present it in the next video. Finally, for the space complexity, as we adopt insertion sort in all sorting phases, shell sort is also an in-place sorting algorithm. In summary, we present the shell sort algorithm in this video. It is also known as the diminishing increment sort algorithm, which precisely describes its procedure. In the next video, we will present a detailed analysis of its time complexity. Thank you for watching, and see you next time.